let's talk about one pin, one force, one muscle, and one bar systems. Now, the diagram that we've described in class here is essentially going to be this guy. You got a pin, you got a bar, you have a muscle, and you got a force. Right? All right, so this engineering diagram describes a bunch of different body systems. Say like the elbow, right? Let's go, say the elbow. This is your hand. You got some weight. Let's say your shoulder is fixed to your body, right? This elbow, we can describe as a pin in 2D. And we can describe this force as just a force acting in 2D, right? Some vector. And when we look at the reaction forces in the elbow, right there, we have to look at the forearm and hand attachment, right? We got to look at the closest thing we have, object or region of interest, that connects our reaction force, right, from our pin to the force that's acting externally, the F, right? So we take that yellow region and we draw it like this. That's easy enough. What else does this thing describe? This thing describes a hip for sure. Right? We got, say, a socket, and we got a femur coming out. So we have some type of force on that femur, right? Well, the engineering diagram, right, and say we have a muscle this way. It's coming from the hip to the femur. We got another attachment in the femur, okay, to the hip. This is a pin. And we want to know what our reaction force is. Okay? Due to some force F acting externally at the knee. So this looks like this whole thing, this engineering diagram, but it's all placed on the side, right? It's all, it looks like this. Pin, force, muscle, right? And so it's the same diagram as this, except this one's rotated. Femur's rotated. Okay. So how do we use this idea, this information, how do we use this engineering diagram to solve all of these problems? Well, we need to make this idea of a general case, right? So let's go describe these points, A, B, C, and D. So that gives us the ability to make vectors to all our forces, right? So we care about RAB, RAC, RCD. We can make these L's, so their length, vectors. And then we care about LAD. Now sometimes we have the ability to just go straight to LCD, right? We can just describe LCD because we know a bunch of points and stuff. All right, we know like the XY coordinate of C and the XY coordinate of D. So we can now say like CD is just the subtraction of these points to find that vector, right? But in most cases, we don't know that. All we know is we know LAB, right? It's like some kind of AB. We know LAC, we call that DC, or I mean CD. So we know how far from the shoulder that this muscle that we're talking about inserts onto the tip, or let's say if this is the humerus, this whole thing is a humerus, then this would be the radius ulna, right? Or in the case of the femur, this would be the femur, and this would be the hip. The whole thing would be the hip, right? Okay. So let's say we know the insertion point of the muscle from the hinge, wherever our hinge is. We call that LAC. So let's say we have also the information of how far from the pin, the connection here, does the muscle insert onto the fixed object. So that's EF. And then let's describe this as length of arm, or forearm. Length vector, okay, let's describe it generally. The length vector from pin to force. or external force. So then this one is LAC. This is length. So length vector from pin to muscle insert on let's say region of interest, right? Okay, and this one is the length vector from the pin to the muscle insert on fixed bone. All right, so in this case, the hip is a fixed bone. We've fixed that bone into place, and we're looking at the femur region of interest, if you want, right? In this case, the humerus is going to be fixed, and we're looking at the region of interest of the forearm and the weight. Okay, so this is how you describe these vectors. Now LCD, if we go just look at vector math real quick, we say LAC is pointing that way. We have LAD pointing this way, and we want a vector pointing from C to D. So we write this out. This was A, C, D, and we know LAD is known, LAC is known. So now we can get C to D, right? That's what we want. And how we do this math real quick is LAD has a vector head to vector head, right? So we say LCD is equal to the vector that has head to head. LAD has head to head with the one we want, LCD. So we say LAD minus the one that has the tail of LCD to the head of the vector we know, right? So that's LAD minus LAC. Let's just do this real quick, right? This EF minus CD, right? LAC, CD, LAD is EF. That equals E minus C and F minus D. Okay, cool. No big deal. So now we've described our engineering system, this diagram with all the lengths, locations that the forces act on, right? Now we need to also describe the forces, and we do that using a free body diagram. So let's make this a little clearer and just clean this whole thing up a little bit. Okay, so the free body diagram of this bar is just going to be some reaction force, some tension force, and some external force. Okay, so then we can write our points down, say A, C, B. We got our coordinate system. Notice that we can choose our coordinate system to be off by some rotation of theta. We could say that this is XY, right? Something like that. And then say like this is theta and that's X prime. And we can, in just our coordinate space, we can do these transformations. So that might be helpful for some problems. But in this case, we're just looking at this like standard deal where the region of interest, the bar of interest, is acting along X, right? We assume that we got static equilibrium. We have rigid bones. We got muscles act in tension only. Okay, and then we have gravity free, because we didn't talk about the weight of the arm or the centroids and stuff. Okay, so that is pretty much it for the engineering diagram and the free body diagram. All we need to do is describe the forces. So let's say this one is R. The reaction force is called R. Say our tension is called T, and then the force external is F. So then F is known. We can write GH. That generalizes those forces. T can be TX component, TY component, and then R can be the same thing. RX, RY. So one thing to point out real quick is that all of our knowns in this whole example have little lowercase letters, where all of our unknowns are going to have these capital letters with a subscript X or Y. And hopefully that helps clean up all this, all the bookkeeping that's needed in these problems. So we've set it up. Now let's go through the analysis. So sum of forces equals 0. Let's go sum of force table. I, J, K, F, T, R. So F is GH, 0. T is TX, TY, 0. T, R, X, RY, 0. Sum here is G plus TX plus RX equals 0. H plus TY plus RY equals 0. And then the 0. So the sum equals 0. And then I kept everything positive here, even though I know tension is acting in the negative x direction. I kept it as just Tx. And that way we can generalize this whole system. We can say that what if we had a muscle that was acting this direction on our free body, where A is the pin? Well, then Tx would be positive. So we're trying to make the general case for this system. And to do that, it's good to keep everything positive. Okay, so step 2. We got sum of moments about something. It's always probably convenient to choose the pin as a reaction. So what do we need? We need the vector that we described. Here's one sticking point that might be a little hard to conceptualize. We could have an arbitrary shape for the bar to a pin, right? And say we had force acting somewhere along these bars, right? We had some force, we had some muscle tension. All we care about to find moments is going to be the pin location to the point the force acts. So we care about this, right? And this is described as L A to B above, and this one is described as L A to C above. Okay, we don't need to take into account anything else because we're assuming this bone is perfectly rigid, right? So I don't really care about the shape of this free body, this rigid bar. It could have a shape that looks like this, right? Where this is the pin, and then some external force acts right there. That looks like the femur, right? And I know my muscle tension goes this direction, so all I need is LAB, and then LA to C, right? That's all I need. So we can check out LA to B cross F and LA to C cross T. Okay, so LA to B was A, B cross GH. LA to C was CD cross TX, TY. Okay, so we do our crosses. Literally A to H gives A cross H gives AH. B cross G gives negative BG. C cross TY, TYC. D cross TY, TX is TX D, and that's negative, right? And remember that that's the reason why is because this is IJ. I cross J is positive K. B cross I is negative K, or J cross I is negative K. So we get a negative out in front. Okay, so we got another equation, right? So step 3, identify knowns versus unknowns, or identify equations versus unknowns, right? Let's go and say equation 1 is G plus TX plus RX equals 0. Equation 2, H plus TY plus RY equals 0. Equation 3, AH minus BG plus TYC minus TXD equals 0. Okay, so how many unknowns do we have? We have TX, RX, TX, TY, RX, RY. Okay. Those are our unknowns. We have 4 of them versus 3 equations. So we need one relationship to finish out the system. Right? So we need need one relation. So then we come back up and we say, okay, we assume the muscle acts in tension only, and we know the direction. The direction is LCD. That's the vector for that's the vector that describes the muscle cable going from C to D. Right. So LCD is E minus C, F minus D. Okay. So so you use muscle okay, so we use this muscle cable idea to find the relationship between T, the vector T, and the components Tx, Ty, right? With L, C to D, vector component E minus C, and F minus D, right? E minus C, F minus D. So let's start off by just saying, what's this relationship? Well, we have LCD vector, and then we have the components of this vector point this direction and this direction. This one is E minus C, this one's F minus D. So then we have some angle that's between them, and that angle can be quickly described as tan of gamma is equal to opposite over adjacent, F minus D over E minus C. We can also describe T in the same way. We could say that T has some angle gamma, and we could say that tan gamma, if this is Tx and Ty, tan gamma equals Ty over Tx. So then we take these and we combine these equations, right? All we do is just plug this in for tan gamma, and we get Ty over Tx is equal to F minus D over E minus C. So that gives us Ty equals Tx, F minus D, E minus C. And there we go. We got another equation. Okay, so make as many relationships as you need on unknowns, and sometimes we have to get creative to make these relationships. So step 5 is going to be make a system of equations. We have these three here, and this one. Okay, so we got to solve for this. Use this one to solve for Rx. Rx equals negative G plus Tx. Ry equals negative H plus Ty. And then let's use this one together to solve for Tx. So we can lump all that stuff together and say, okay, so let's clean this up a little bit before we move on. And then let's just make this one Ty equal to Tx times some variable beta. And let's just write beta down real quick. That's the first thing beta equals F minus D over E minus C. Okay. And let's solve everything else. Let's go solve for Tx here. So we got Tx D equals AH minus BG plus TYC. Okay, so let's do another simplification real quick. Just say that we plug in this guy into here. So we get Tx D equals AH minus BG plus Tx beta C. All right, let's bring these things to the one side real quick. We got Tx D minus beta C is AH minus BG. So then Tx equals AH minus BG over D minus beta C. Let's describe all that stuff as one other variable. Let's say Tx is equal to eta. So then we can write eta here. It's AH minus BG over D minus beta C. And now we write simply Tx equals eta. Now we can write Ty equals beta beta. And then we have Rx, Ry that we need. So Rx negative G plus eta, Ry negative H plus eta beta. And there we go, that's our system. So we got to solve this thing in this direction, right? Go beta to Ry. And now we have to think about how we use this in a general case, right? So let's say we have some muscle system that when we draw the engineering diagram, this is remember, the system of equations here for one bar, one muscle, one force, one external force, right? So, like, it's not good enough to say this is the system of equations for something like one bar, one muscle. You need to remember that this is the system for all of these cases. You have one external force, one pin, one bar, one muscle. And it's easy to adapt this to more external forces, but we can see, you can just kind of do this whole entire analysis again with two external forces and see how the system of equations change. And you can make a general case for a number of external forces if you want, right? So let's say we have some pin, we have a bar acting in some direction, we have some cable, and we have some external force. And we want to just quickly use this system of equations to study this problem, right? So we can name our points. We say this is A, that's B, that's C, and that's D. And then we simply just use our vectors, LAB, LAC, LAD, LCD. We find the components of these vectors, I call them AB, CD, EF, do our vector subtraction, and that's going to be E minus C and F minus D. We find our forces, we got F, call that GH. Okay, and that's, what else do we need to know, right? Everything else is going to be solved for us. So if we can write all of these variables, we can use them to plug them into this equation, system of equations, and the directions and magnitudes of all the force vectors should pop out, right? So that's basically it. You can do this kind of general analysis for any system that you can describe by like a set of ideas, right? Set of how many muscles are acting, how many what do you have? You have a pin, you have a fixed connection, you have a roller, all these things are going to change the system of equations. But once you identify that your system looks like this, or you simplify your system to look like that, you can just simply use these vector variables to solve for the reaction forces in the cable and in the pin. Okay.